In this video, I want to take a look at how to find the work as a result of a spring force. And you guys are going to see that this is a little bit more tricky because force depends on displacement. All right, so the spring force is governed by something called Hooke's law, which looks like this. Okay, this says that the spring force, right, is equal to the negative, right, which makes sense because anytime like I pull a spring, right, let's say I have this and like I pull a spring this way, this is my F, I'm like yanking, right? The spring force, the force of the spring, always goes the opposite direction, and that's what that negative sign means, okay? So the spring force is equal to negative something called the spring constant, right? Which is basically just a constant that determines the stiffness of the spring, right? You know that some springs they're really much harder to pull, right? And that's a higher spring constant. And then X here is the displacement. That's how much you actually have moved that spring, okay? Which makes sense, right? How much force is on a spring should be determined by how stiff it is and how much you actually stretch it, okay? That's the stiffness, that's how much you stretch it, okay? Now, remember that work in general is equal to F dot D, right? That times your displacement. In this case, the displacement is X, right? How much you're pulling it, right? But things get confusing when F depends on D. You can't separate these, right? In this little guy. So you have to use a little calculus trick, right? And say that the differential of work, any little differential of work, is equal to your force times, or dotted with your dx, dotted with some little infinitesimal displacement that you're doing, right? And so that means that your work is actually going to be the integral of your spring force, which in this case is negative kx dot dx, right? But the integral of negative kx is 1/2 kx squared. Okay, you guys probably remember the constant will come on the outside there, and when you integrate a variable, you raise the power and then divide by that power, so you get 1/2 kx squared, okay? And the negative stays. So the work done by a spring force is just this guy right here, okay? And this has lots of cool biological applications because essentially your tendons in your body are all springs, right? And they're all doing the work of a spring force on your bones, okay? So let's take a closer look at that. If you guys could go to the slide that says work done by tendons, okay? It says the Achilles tendon has a spring constant of about 200,000 newtons per meter. That's really, really big. It's very impressive, which is amazing for something made of organic compounds. In fact, it's hard to believe that they ever tear, right? Sometimes it seems like Achilles heels tear so easily. So with a spring constant like that, how the heck does that happen? Well, there's a lot of other biological factors at play when that happens, and physical factors, but that's not what we're doing here. In the process of standing on your toes, right, getting on your tippy toes, the muscle extends about 4 inches. My question is, how much work does that tendon do on your foot during that extension, okay? So I want to know, how much work does that tendon do on my foot? So remember that work, right, is equal to the work due to a spring, and I'm considering the tendon here being a spring to be 1/2 kx squared here, okay? And I'm going to replace this s with t for tendon, the work done by the tendon, okay? Well, we know that the spring constant is about 200,000, give or take, newtons per meter. And I'm saying that the extension was about 4 inches. I would love to do a conversion here. 4 inches is about, well, I know that 1 inch is equal to 2.5 centimeters. Okay, so 4 inches would be about 10 centimeters, which is about 0.1 meters. Is that accurate? I think so. Okay. And so that means that the work that this tendon does is 1/2 times 200,000 times 0.1 squared. Okay, and so let's see if we can do this without a calculator. Okay, let's see if we can just totally not be so reliant. 200,000 divided by 2 is just 100,000, right? And then 0.1 squared is just 0.01, right? So if I multiply 0.01 times 100,000, really all I'm doing is I'm moving the decimal place over twice. So I'm moving it once, twice, and I get about 1,000 joules. Okay, so the work that tendon is doing on during that extension is going to be about 1,000 joules. Okay, so that's part A. Part B is how much work does gravity do in the rise, right? So if this is your foot, right? So here's your little heel. That's not terrible, right? Remember, in this case, there's a force going up that your tendon is pulling. We'll call that T, right? And then there's this force going down. That's, the weight of your foot, right? Okay. So remember, this guy is just a normal, nice force that's not dependent on displacement. So you can do your famous old work is just equal to F dot D, right? Your force vector times your displacement. This time, force is your weight. So this is the work done by gravity. So your force is weight, which is mg, times the displacement, times cosine of the angle between them, right? Now, weight's down, but your displacement's up, right? You're getting up on your tippy toes, right? So if displacement's up, the angle, again, is this 180 degrees, right? So this will be the mass of the foot, which I approximate here to be about, let's say, I don't know, what is a typical foot? A kilogram? Okay, so I'm going to say 1 kilogram, okay, times 9.8 times the displacement, and we said the displacement is going to be about 0.1 meters, right? Times cosine of 180, which makes this all negative, okay? So I'm going to, again, attempt to do this without a calculator, right? 1 is just 1. Multiplying 9.8 times 0.1 just moves the decimal place over a little bit, right? And so I get 0.98 joules there, okay? Now, that is the work that gravity is doing on the foot during that little rise, all right? So the question again is, what is the network? And by the way, this will be negative. What is the network? Again, I just subtract the work done by gravity by the work done by the tendon over here, right? And I get roughly 999 joules, right? Now, to be clear, I've made a lot of simplifications here. I've tried to boil this down into the simplest way possible. Biological analysis or physical analysis of biological systems is not always this easy, but I wanted to give you kind of an idea of how this applies to the human body, okay? My question for you now is, now that you know this this net work that I've done, could you use the work energy theorem to find out what the velocity would be of your foot at the top of its rise on this tippy toe rise, okay? Again, it'll be an approximation, but I'm curious to see what you come up with. In the next video, we will be wrapping up with a misconception question, and that'll be all for this part of energy, and we will return to energy again next week.